this is the circuit of a generalized impedance converter. This circuit is called impedance converter because this circuit can behave both all like all the passive components that are resistors, capacitors and inductors. So the way it behaves is, for the inputs voltage source, the voltage source, this whole circuit either behave like a resistor, capacitor or inductor based on the values of Z1 to Z5. So we can change these values and simulate each of the passive component. The way it behaves is, see, this circuit has active components like active components like an op amp. So this is an active impedance. You might have also seen active rectifier. So a basic rectifier contains a diode, which is a passive component. An active rectifier consists of what is called an active diode. An active diode is a combination of a diode and a MOSFET or an op amp to enhance its working. So similarly, these impedance converters are behaves like an active impedance. So it it certainly does not in like work like a active device, that is, it supplies some power. It by nature it's a passive device, but just in by the involvement of active devices like op amp, it enhances its properties. So the let's start by analyzing the circuit, and then we will go to like uh, going through an example of how it works. Okay, so you see the two op amps M1 and M2. I have named it so. Now we can by seeing the circuit itself, we can make sure that both the op amps are in negative feedback, because the feedback loop is only contains passive elements Z3 Z. This feedback for the M1, for the op amp and M1, the feedback loop contains only Z3, which is a passive element, and for transistor for the op amp M2, the feedback loop is this, and it contains Z2, which is also a passive element. And we can happily be certain of that the both the op amps are in negative feedback. And because they are in negative feedback, we can apply the concept of virtual short in the op amps. Please make sure that while analyzing any op amp circuit, please make sure that you are applying virtual short only when the op amps are in negative feedback. Otherwise, the virtual short concept is not applicable, and you might go wrong with the answer. So now that we have confirmed it, we can happily apply virtual short, and this means the voltage here, that is the input voltage Vn, can be uh, like the voltage here for the op amp at the at the non-inverting terminal, the voltage will be Vn, and by the virtual short concept, the voltage at this node will also be Vn. And similarly, uh, like I am assuming the output of op amp 1 as V01, VO1 or V01, whatever you call it, and the output of op amp 2, I have named it V02. Now we need to the basic idea behind the analyzing the circuit is, see, for the voltage source Vn, some current In will flow, and by the Thevenin's equivalent, if we replace it with the Thevenin's equivalent, the Thevenin's resistance will be the Thevenin's impedance, if we would call it. The Thevenin's impedance would be Zn, would be Vn upon In. So we are basically finding In to see how the Vin is. Okay, so Vin, if it comes in the form of resistances, it acts like a resistance. If it comes in some form of j omega, times some value, it behaves like a inductor. If it comes like 1 by j omega something, it behaves like a capacitor. And apart from these two, we can simulate second order impedances also. So that will be a bit deviating from the concept. Let's focus on analyzing it. So both the outputs are output of op amp 1 is V01, output of op amp 2 is V02, and in order to find the current V in, we can what we can do is, see, we can happily write V Z input as V in upon In, and the I in, we don't know I in, so we can write it as V in minus V naught. Let's assume the current is flowing in this direction, so V in minus V naught 2 upon Z1 will be the input current, and by substituting it in this formula, we will get Zn. Now let's go back to analyzing the circuit. Okay. Yeah. So yeah, because we know that the virtual short is being applied, and the op amp is in negative feedback, the op amp will not take any current. So um, here the op amp is not taking any current, so and also this op amp is not taking any current, so the current through flowing through Z2, assuming it is in downward direction, the current through Z2 will be equal to current in Z3. So from this, this is one such condition, and also the current in Z4 and Z5 will be equal because the op amp is not taking any current, so both the current flowing in both the impedances will be same. So current in Z4 and Z5 will be equal. Now assuming like considering this, we can write the KCL equation, that is current through Z4 will be equal to current through Z5. Current through Z4 will be V naught 1 minus Vn upon Z4, that is this, and the current through Z5 will be Vn minus 0 upon Z5, that is this. So, and the current through Z4 and Z5 are equal. So okay, sorry, I should have written this in here. So this equation is related to this, and this equation, the KCL equation, is related to this part. Okay, so the current through Z2 and Z3 both are equal, and we can happily write the KCL equation at that node, this particular node, V02 minus Vn upon Z2, which will be same as Vn minus V01 upon Z3, which is corresponding to this equation. Now that we have got both of it, we actually want Vn minus V02 upon Z1. So we don't want V01 in any of our equations, the finalized equations. So we have to somehow eliminate V01. Now seeing this equation, we can write V01 as something, some V in times something. Okay, and if we get V01, we can substitute it in this equation, which will be in the relation between V02 and Vn, and we can then apply this the obtained equation in this equation. Now let's not get deep into solving the equations. It is very simple. The V0, by solving this, you get V01 as Vn times 1 minus Z4 upon Z5, and by substituting it in all of that and performing the subsequent analysis, you will get Vn in terms of in terms of Vn. Okay, Vn times something, and therefore finding Zn as Vn upon In, you will finally get Zn, or the input impedance that is seen by this voltage source. So the voltage source, let 1 minute. So the voltage source, the input, the impedance seen by this voltage source. Okay, so this voltage source sees an input impedance of Zn. Okay, so looking through these two terminals, this part, the input impedance is Zn, and the Zn from the analysis came out to be Z1, Z3, Z5 upon Z2, Z4. So this is the final equation for the input impedance. Now, as mentioned before, let's perform some a basic analysis. Let's assume Z1, Z3, Z5 are resistors, and any one of Z2 or Z4 is a capacitor. Okay, and the other one is a resistor itself. Now I am assuming Z4 as a capacitor of value C, and the impedance of a capacitance is given by 1 by j omega C. Okay, and because the others are resistors, I can simply write as some resistances. Now if we the equation Zn is in this form, and if we rearrange, it gives us some relation like an inductor. Okay, so after rearranging, we get j omega times some value. Okay, so it is similar to impedance of a inductor. So for inductor, the impedance is j omega l. So the l is this value, and by changing r1, r2, r5, c and r2, we can tune the value of the inductor. Okay, so we have not actually, mind you, we have not actually used an inductor, but the voltage source v in sees that the assumes like, or it the circuit behaves as if this whole part is replaced with an inductor of value L, which is given by uh, this thing. Okay, so the whole circuit behaves like a, so here is the voltage source v in, the the whole circuit behaves like as if there is an inductor of value L, which is R1, R3, R5, C time upon R2. So this is the value of inductor, and the whole circuit behaves like a inductor. uh, as mentioned earlier, we can not only simulate basic passive components that are resistances, capacitance and inductance, we can also use second order impedances that are like, in Bode plots you might have seen, if there is a, term s square, if there is an s square term in the denominator, the Bode plot will roll off by 40 dB, 40 dB per decade. And if the numerator has some s square term, then the Bode plot will rise with the what the slope of the curve will be 40 dB per decade. And that is the basic functionality of this impedance converter. It has also, it is a very important thing in precision based circuits also. So, and thank you.